Before we start the more complicated stuff here, we need to make sure that we remind ourselves how a galvanometer works. I have a power supply hooked up to a resistor so that I don't go off scale on the galvanometer. I have positive going into the positive side. I have it at 1.5 volts, the lowest that it possibly has, and it reads positive. If I were to take this and I were to put the positive into the negative, it reads negative. Therefore, whichever end the positive current flows into, it pushes that direction. If positive goes into the red side, it moves to the right. If positive goes into the left side, it moves to the left. Here's a handheld generator. Watch what happens when I turn it. I get electricity out. No surprise there. But I would like you to see this. When I let go, it stops very quickly. Okay, there's resistance to me moving the electricity through those wires. This motor right here has magnets in it, and I'm moving wires through the magnets. So when you move a wire through a magnetic field, through magnetic induction, it produces current, but it tries to resist that motion. So the force is actually resisting it. You should know which way that is. Now if I disconnect it, so right now there's no current being produced. Watch what happens here. That's easy to push because there's no resistance to those wires producing current. So let's figure out the actual direction of the resistance. So what is the direction of the current coming out of this generator when I turn it clockwise? Well, you notice that I have it hooked up now to the galvanometer with the blue going into the red. Okay, so let's see what happens. And it reads positive. So once again, we have just proven that if I move this clockwise, the galvanometer reads positive, which means current is flowing out of the blue wire. I now have the power supply hooked up to the hand generator. And I have the blue, which we said was the positive, hooked up to black. And you might say, that makes no sense. I thought that was the positive current. Remember, we said that positive current was coming out of the blue end. Positive current was coming out of the blue end, and this was moving when this was moving clockwise. Well, if I want current to come out of the blue, forced through with the battery, I need it to go into the opposite. It goes into this one and out of the blue. So red to black, into the opposite side, out the blue. Now let's see what happens here. Before, when we had current coming out of the blue end, this moved clockwise. And now it's moving counterclockwise. What does that prove? It proves that when current is coming out of the blue end here, there's a resistive force trying to move this the opposite direction. That's why it was resisting me when I moved it. So now we've got a wire moving through a magnetic field producing current, which is called an induced current. These are the charges in the wire that are all moving that direction. Now, we all know that negatives move in wires and not positives. This was proved at the end of the 19th century, Hall's effect. However, all of the concepts work the same, and the AP board and most physics books, actually all physics books that I know of, follow positive current flow. These positive charges are being moved by an external force. This external force moves the wire to the right. We put our fingers pointing into the page. The wire is moving to the right. That's my thumb. My palm is facing to the top of the page. That would be the direction of the magnetic force in the wire. You can see it right there. That's the direction of the magnetic force, upwards. Well, this magnetic force produces a current and an EMF, an induced current. Now that we have the charges moving this direction, that's a different right-hand rule. We point our fingers again into the page. The current is flowing to the top of the page, and there's a force this direction. This is a magnetic force on the induced current. This is the direction of the force on the moving wire, inside the wire. That produces current going this direction, which itself feels a back force going opposite the direction it was moving. This has to be, because if we're producing current in the wire, as you saw in the generator, it's producing electrical current. Electrical current is electrical energy. Energy has to come from someplace. So this external force is actually doing work. This work produces a current. Well, if I'm pushing out of this direction, then there has to be a force resisting it. That's the resisting force. Another way to look at this using conservation of energy. Let's imagine that we had a magnetic field going this direction, and we had a wire. We had a set of rails going this direction, and we have a wire that's rolling down. If the wire is moving down, then potential energy is becoming kinetic energy, which is becoming electrical energy. Now that electrical energy has to come from the kinetic energy, so that as the electrical energy is being produced, the wire is slowing down, so there must be a force going opposite the direction it was moving. Let's check that with a right-hand rule. First of all, magnetic field up, the wire is moving to the right, so there would be a current in the wire out of the page. That current itself feels a magnetic force on it. Magnetic field to the top of the page, current in the moving wire pointing to the outside of the page, which produces a back force trying to stop the wire.